February 19th, 1942. Dawn over Darwin Harbour. The tropical air hung thick and still at 88 degrees Fahrenheit, carrying the smell of salt water and aviation fuel. On the deck of the USS William B. Preston, 23-year-old lookout James Mitchell raised his Navy-issue binoculars to scan the northern horizon, a ritual he performed hundreds of times without incident. Except this morning, the binoculars revealed nothing but blur. The optical glass, imported from Germany before the war, ironically, had begun to delaminate in the humidity. Fungus crept between the lens elements. Mitchell squinted through compromised optics at a sky that should have been empty. At 9:58 a.m., 188 Japanese aircraft appeared overhead. He never saw them coming in time. The first wave struck with devastating precision. Dive bombers screamed down at 350 miles per hour. 8 ships sank. Military installations erupted in flames. At least 243 people died in what would become the first of 64 Japanese air raids on Australian soil. And across the northern defence perimeter, on vessels and observation posts stretching from Perth to Cairns, hundreds of Australian and American servicemen peered through faulty, fungus-infected or completely absent optical equipment. Australia faced a catastrophic reality. The island continent possessed not a single facility capable of producing military-grade optical glass. Every binocular, every bombsight, every rangefinder, every periscope, every gun sight, every reconnaissance camera lens, all depended on imports that no longer arrived. British factories struggled to supply their own forces. American production prioritized the European theater. Japanese submarines prowled the sea routes, sending supply ships to the bottom. The strategic arithmetic was merciless. Japan controlled French Indochina, Malaya, Singapore, the Dutch East Indies, and much of China, territories containing most of the world's high-quality silica sand deposits. German optical manufacturers like Zeiss and Schott had spent decades perfecting glass formulations, their expertise now enlisted for U-boat periscopes and Luftwaffe bombsights. Australian forces defending 7,692,024 square kilometres of territory did so increasingly blind. But in a converted jam factory 30 kilometres south of Sydney, a 47-year-old Hungarian refugee who'd fled fascism, with nothing but technical drawings sewn into his coat lining, was about to change the calculus of the Pacific War. His name was István Auer, though he'd begun calling himself Stephen after arriving in Melbourne. He'd already failed twice to convince government officials that he could solve their optical. The third attempt would either save Australia's defence or consume his life savings in a spectacular failure witnessed by military intelligence officers who'd placed surveillance on his workshop, unsure whether he was a genius or an Axis spy. This is the story of how one immigrant's obsessive understanding of silicon dioxide molecular structures created an entire industry from nothing, how his secret factory produced 1.2 million precision optical components under conditions that violated every known manufacturing principle, and how Australian soldiers went from near blindness to optical superiority over Japanese forces, all within 18 months of that catastrophic morning in Darwin. István Auer entered the world on March 14, 1895, in Budapest, when the Austro-Hungarian Empire still stretched across Central Europe and Hungarian science flourished in a golden age. His father, László Auer, operated a modest lens-grinding workshop serving the city's opticians and camera makers. The family lived above the shop on Vaki Street, where young István fell asleep each night to the rhythmic sound of grinding wheels against glass, a mechanical lullaby that would shape his destiny. Budapest at the turn of the century produced an extraordinary concentration of scientific talent. The same neighborhoods that raised István also produced physicists like Leo Szilard and Eugene Wigner, mathematicians like John von Neumann, and engineers whose innovations would reshape the 20th century. Something in the culture, perhaps the fusion of German technical education, Hungarian linguistic precision, and Jewish intellectual tradition, created an environment where asking why wasn't just permitted but expected. István asked why, obsessively about glass. At 14, he'd already read every text in his father's library about optical theory. At 16, he conducted unauthorized experiments in the workshop after midnight, trying to understand why certain glass compositions refracted light more efficiently than others. His notebooks from 1911, later donated to the University of Melbourne archives, contain remarkably sophisticated calculations about refractive indices and dispersion coefficients, work that would have been impressive for a university researcher, let alone a teenager working by candlelight. The Great War interrupted everything. István spent 1914 to 1918 in an Austro-Hungarian artillery unit, where he encountered military optical equipment for the first time. The rangefinders that calculated target distances, the periscopes that allowed observation from trenches, the telescopic sights that guided artillery fire, all these instruments fascinated him more than horrified him, though he witnessed plenty of horror. He studied captured Russian and Italian optical equipment, noting the superior quality of Italian glass, the clever mechanical designs of French instruments. Demobilized in November 1918 into a Hungary that had lost two-thirds of its territory and faced revolutionary chaos, István returned to find his father's workshop looted, the grinding equipment stolen or destroyed. Laszlo had died during the Spanish flu pandemic. At 23, István inherited a business that no longer existed and a country descending into economic collapse and political extremism. Rather than rebuild in Budapest, he migrated west to Vienna, where the famous optical firm Carl Zeiss had established a subsidiary. He arrived with strong recommendations from his army commanders who'd observed his technical abilities. Zeiss Wien hired him as a junior optician in 1920. For the next 9 years, István learned the secrets of precision optical manufacturing from German masters who guarded their knowledge like medieval guilds guarded trade secrets. The critical breakthrough came in 1927. Working on a special order for astronomical telescope lenses, István discovered that adding specific ratios of barium oxide to the standard glass formula produced superior light transmission characteristics, particularly in the blue spectrum, crucial for astronomy. He documented the process meticulously, exactly 12.3% barium oxide, heated to 1,420 degrees Celsius, held at temperature for 7 hours, then cooled over 14 days at precisely controlled rates. Deviation by even 10 degrees or 30 minutes compromised the results. Zeiss Wien applied for a patent with István listed as co-inventor. Patent AT 142786, filed April 3, 1928. Described Hochdurchlässiges Glas für optische Anwendungen. István's name appeared in the technical literature. He'd become, in a small way, somebody in the world of specialized optical manufacturing. Then the darkness descended. The Austrian political climate deteriorated through the early 1930s. By 1936, anti-Semitism had moved from beer halls to government policy. István, though not particularly religious, bore a Jewish surname and heritage. Colleagues who'd worked beside him for years began avoiding eye contact. In February 1938, Austrian Chancellor Kurt Schuschnigg attempted to resist Nazi pressure through a referendum. In March, German troops crossed the border. The Anschluss made Austria part of Hitler's Reich overnight. István had perhaps 2 weeks before the roundups began. He packed a single suitcase, sewed copies of his patent documents and formulas into his winter coat's lining, and purchased a ticket on a passenger ship departing Genoa for Melbourne. Why Australia? Because the Australian government, critically short of skilled immigrants, had eased restrictions for refugees with technical qualifications. István carried letters from former Austrian army officers, Gentiles who remembered his competence, attesting to his engineering expertise and loyalty. 1-2-30. He arrived at Station Pier, Port Melbourne, on September 7, 1938. Age 43. Profession: optician. Assets: £127 in savings, a suitcase of clothes, and formulas for glass compositions that would soon become critically important to a nation that didn't yet know it was about to enter a war for its survival. István, now Stephen to Australian immigration authorities who struggled with Hungarian names, spent his first year in Melbourne working at a small optical shop in Carlton, grinding prescription lenses for eyeglasses and repairing cameras. The work paid £4 per week, enough for a rented room and meals, but nowhere near enough to establish his own facility. He spent evenings writing to government departments, universities and industrial companies, explaining that Australia possessed no capacity to manufacture military optical glass, and that war seemed increasingly likely. Every letter received polite dismissal. This wasn't unusual skepticism. British colonial attitudes still dominated Australian industry in 1939. The prevailing assumption held that sophisticated manufacturing belonged in Britain or America, while Australia produced agricultural products and raw materials. The idea that a middle-aged immigrant working in a Carlton lens shop could establish military-grade optical production. Then came September 3, 1939. Prime Minister Robert Menzies' radio address, Great Britain has declared war upon Germany, and as a result, Australia is also at war. The declaration transformed Stephen's obsessive letters from crank correspondence to prophetic warnings. Within weeks, British optical supplies to Australia began to diminish, diverted to desperate needs in Europe. Within months, they'd nearly ceased. The Australian military establishment faced a crisis they'd barely contemplated. Every modern weapon system required optical components. Field artillery used rangefinders that measured distances up to 15,000 yards. Anti-aircraft guns employed height finders and tracking instruments. Naval vessels carried searchlights with focusing lenses 3 feet in diameter. Aircraft needed bombsights, navigation instruments, reconnaissance cameras. Infantry required binoculars, rifle sights, signaling equipment. Coastal defense installations depended on powerful observation telescopes. A modern binocular contained 8 to 12 precision ground glass elements, each requiring different optical properties. The objective lenses needed crown glass with specific refractive indices around 1.52 and low dispersion. The prisms demanded dense flint glass that could bend light through exact angles without chromatic aberration. The eyepieces used special formulations that provided comfortable viewing without distortion. Every element required glass free from bubbles, striations, and color variation, defects measured in parts per million. Germany's optical supremacy rested on more than a century of development. Schott Glassworks in Jena had pioneered the science of optical glass composition beginning in the 1880s. Working with physicist Ernst Abbe and optician Carl Zeiss, chemist Otto Schott had systematically tested thousands of glass formulas, creating a catalogue of specialized optical glasses with precisely documented properties. By 1939, German manufacturers could select from over 100 distinct optical glass types, each optimized for specific applications. The United States, recognizing its dangerous dependence on German optical glass, had established emergency production at Bausch and Lomb and Corning Glass Works in the 1930s. By 1940, American factories were producing military-grade optical glass, but every ounce went to American forces or Britain. Australia's requests received sympathetic responses and low priorities. American merchant ships crossing the Pacific faced increasing Japanese submarine activity. The first Australian orders for optical glass, placed in late 1940, hadn't arrived by mid-1941. Some never would. Japan's position was stronger than many Allied Japanese optical companies like Nippon Kogaku KK, later Nikon, had licensed German technology in the 1920s and expanded production through the 1930s. By 1941, Japanese military forces possessed excellent optical equipment, often superior to early war American gear. Japanese binoculars captured in early Pacific battles impressed Allied technical analysts with their quality. The fall of Singapore on February 15, 1942, sent shockwaves through Australian defence planning. If Britain's impregnable fortress could collapse in mere days, what protection did Australia have? Japanese carrier groups roamed the Pacific with apparent impunity. 4 days after Singapore fell, Japanese aircraft devastated Darwin. On February 24th, Japanese submarines surfaced off Sydney Harbour, demonstrating how vulnerable Australian cities were to naval attack. Australian Prime Minister John Curtin's March 1942 statement captured the existential crisis. We refuse to accept the dictum that the Pacific struggle must be treated as a subordinate segment of the general conflict. Translation: Britain couldn't or wouldn't defend Australia. America was reeling from Pearl Harbor. Australia stood effectively alone against Japanese forces that had conquered everything from the Indian Ocean to the Central Pacific. In this desperate context, István Auer's persistent letters to the Department of Munitions finally reached someone willing to listen. That someone was Ernest Stanley Burberry, a 56-year-old engineer who'd been appointed Director of Ordnance Production. Burberry's background in manufacturing gave him practical understanding of production challenges. Unlike the university-educated administrators who dismissed Stephen's proposals, Burberry recognized that orthodox approaches had failed and that unorthodox solutions deserved consideration. Their first meeting occurred on March 11, 1942, in a Department of Munitions office in Melbourne. According to Burberry's later account, archived in the Australian War Memorial Collection, Stephen arrived with a battered briefcase containing patent documents, chemical formulas, and production diagrams. For 90 minutes, Stephen explained exactly how to establish optical glass production from nothing, the equipment needed, the raw materials required, the technical obstacles and solutions, the production timeline. the costs. Burberry was convinced but cautious. The proposal required £15,000 in initial funding, roughly $1, $8 million in modern terms, with no guarantee of success. The chemistry was complex. The engineering was demanding. And István Auer, despite his credentials, was still an immigrant who'd arrived just 4 years earlier from a country now allied with Australia's enemies. Security concerns weren't paranoid. German intelligence had infiltrated Australian institutions, and fifth column fears ran high after Darwin's bombing. The compromise was careful validation. István would receive £500 immediately to conduct proof-of-concept experiments. If successful, full funding would follow, but security restrictions would apply. No publicity, no unauthorized visitors, regular inspections by military intelligence. István agreed instantly. After 3 years of rejection, someone finally believed the crisis was solvable. He found suitable premises almost immediately. A 2-story brick building in Marrickville, an industrial suburb south of Sydney. The structure had most recently housed a jam factory that had gone bankrupt. It offered 8,000 square feet of floor space, adequate electrical service, water supply, and loading docks. The location was perfect, close enough to Sydney for material deliveries but obscure enough to avoid attention. István signed a lease for £12 per month on March 28, 1942. What happened next would either vindicate István's confidence or confirm his critics' skepticism. He had 6 months to prove that a jam factory could become an optical glass production facility capable of supplying Australia's entire military requirements. The alternative, continued dependence on imports that rarely arrived, meant Australian forces would fight increasingly blind as existing optical equipment failed, was destroyed in combat, or couldn't be replaced. The clock was running. Japanese forces were consolidating control over New Guinea, just 150 kilometers from Australian territory. Every week brought reports of Allied optical equipment failures due to tropical conditions, enemy action, or simple exhaustion of pre-war stocks. And in Marrickville, in a building that still smelled faintly of raspberry preserves, István Auer began the most intense engineering challenge of his life. The fundamental problem of optical glass manufacturing is that glass wants to be imperfect. Molten glass, that viscous liquid at 1,500 degrees Celsius, desperately wants to trap air bubbles, incorporate dust particles, develop uneven composition, crystallize during cooling, and stress itself into useless warping. Nature opposes optical perfection at every stage. Creating military-grade optical glass requires fighting nature with obsessive precision at every step. István began with raw materials. Optical glass starts with silica sand, but not just any sand. Common beach sand contains iron oxide impurities that tint glass yellow or green, unacceptable for precision optics. István needed sand with iron content below 0.01%, impossibly scarce in Australia, where geological conditions favored iron-rich deposits. He spent 2 weeks traveling to mining regions testing samples before locating acceptable deposits near Kalgoorlie in Western Australia. The sand had to be shipped 3,400 kilometers to Sydney, ground to powder in ball mills, then washed repeatedly in hydrochloric acid to remove remaining iron traces. The chemical additives posed equally difficult challenges. Optical glass requires exact proportions of compounds like soda ash, sodium carbonate, potash, potassium carbonate, lime, calcium oxide, barium oxide, and lead oxide, each affecting refractive index, dispersion, and durability. István needed analytical-grade chemicals with 99.9% purity. Australian chemical suppliers in 1942 primarily served agricultural and mining industries, not precision optical work. He eventually located suitable suppliers, but at costs 3 times normal due to wartime scarcity and his small order volumes. The furnace construction consumed 6 weeks and most of István's initial £500 budget. Optical glass furnaces must maintain temperatures between 1380 and 1480 degrees Celsius, with variation under 5 degrees precision that standard industrial furnaces couldn't achieve. István designed a custom furnace using principles he'd learned at Wien, a refractory brick chamber lined with platinum sheeting to prevent contamination. Electric heating elements wound in specific patterns to create uniform heat distribution, and a sophisticated temperature control system using thermocouples and rheostats. Building this required skills István didn't possess. He hired Harold Yates, a 52-year-old refractory brick mason who'd worked on industrial furnace construction and Thomas Chen, a 38-year-old Chinese-Australian electrical contractor experienced with high-temperature installations. Both men thought Stephen's specifications were impossible. Yates later recalled, "He wanted temperature control tighter than any commercial furnace I'd seen. I told him it couldn't be done. He showed me the mathematics proving it could. We built it anyway, expecting failure." The furnace first achieved operational temperature on May 19, 1942. Stephen's notebooks record the moment with characteristic precision, 1437 hours. Temperature 1425 degrees Celsius. Variation plus 3 degrees Celsius, stable. Below this, he'd written simply, "Funktioniert," German for, "it works." That evening, he loaded his first experimental batch, 20 kilograms of mixed raw materials in a platinum crucible, the formula representing his best estimate of a general-purpose optical glass composition suitable for binocular lenses. Optical glass doesn't simply melt and become useful. The molten mixture must be held at temperature for 6 to 8 hours, while gases escape and chemical reactions complete. Then begins the critical annealing process, controlled cooling that prevents internal stresses. Stephen's formula required cooling from 1425 degrees to 400 degrees over exactly 8 days, following a logarithmic curve that he'd calculated to minimize stress while avoiding crystallization. Too fast, the glass shatters from internal tension. Too slow, crystals form, ruining optical properties. The first batch emerged on May 28, 1942. Stephen let the furnace cool naturally overnight, then opened it, with Yates and Chen present as witnesses. The platinum crucible contained roughly 17 kilograms of dark green glass, the color immediately indicating excessive iron contamination. Stephen poured acid-washed sand onto the laboratory bench, examined it under magnification, and discovered microscopic iron particles the washing hadn't removed. The iron content was perhaps 0.03%, invisible to casual inspection but fatal to optical quality. Batches 2 through 7 suffered various failures: bubbles, striations, crystallization, cracking during cooling. Each failure taught Stephen something about how Australian materials and conditions differed from Austrian ones. The atmospheric humidity affected how hygroscopic chemicals absorb moisture. The electrical supply voltage fluctuated more than Vienna's had, requiring better regulation. The local refractory bricks outgassed differently than European ones, contaminating the glass. By batch 8, Stephen had adapted his processes to Australian realities. He modified sand washing procedures, adding a magnetic separation stage that removed iron particles. He rebuilt the furnace temperature controller with imported German-made rheostats, expensive and difficult to obtain, but necessary for precision. He adjusted cooling curves based on how Australian ambient temperatures affected the furnace's heat loss rate. On June 23, 1942, batch 8 emerged, clear, colorless glass with no visible bubbles or inclusions. The acid test, literally, came next. Stephen cut sample discs, ground them parallel, and measured optical properties using a refractometer borrowed from the University of Sydney. The refractive index measured 1.523, within 0.0002 of his target. The Abbe number, measuring dispersion, came to 58.6, acceptable for crown glass. He examined samples under polarized light, looking for stress patterns. Nearly stress-free. He tested chemical durability by immersing samples in weak acid, excellent resistance. Ernest Burberry visited on June 29th, accompanied by 2 military intelligence officers and an optical engineer from the Royal Australian Navy. Stephen demonstrated his process, showed test results, and presented 2 sample binocular lenses he'd ground from batch 8 glass. The naval engineer examined them with professional instruments, checked them against specification sheets for British military binoculars, and pronounced them acceptable. Not perfect British glass, had slightly better properties, but definitely acceptable for military use. Burberry authorised full funding that afternoon, £15,000 for equipment, materials and operations, with monthly production targets ramping from 100 kilograms in August to 500 kilograms by December. Stephen now faced the enormous challenge of scaling from experimental production to industrial output while maintaining quality. Every instinct he developed in precision optical work emphasized small batches and careful control. Now he needed mass production. He recruited his workforce carefully. Australia's skilled labour had been drafted into military service or absorbed by munitions factories building artillery shells and aircraft parts. Stephen needed people who could learn precision work, but weren't already committed to war production. He found them in unexpected places. 3 women who'd worked in pharmaceutical compounding, understanding chemical precision. 2 Chinese immigrants who'd worked in restaurant kitchens, accustomed to exact temperatures and timing. A German Jewish refugee who'd been a chemistry professor in Berlin. A deaf Aboriginal man with extraordinary visual discrimination who became Stephen's best quality inspector. By August 1942, Stephen employed 14 people. By October 23, by year's end, 37. The workforce was deliberately diverse, a practical necessity given labor shortages, but also Stephen's conscious choice. He'd fled fascism's racial ideology. His Australian factory would operate on competence, not background. Workers received above-average wages, £6 per week compared to £4, £5 typical for factory work. In return, Stephen demanded absolute precision and reliability. August 1942, 127 kilograms. September, 286 kilograms. October, 441 kilograms. The quality remained remarkably consistent. Rejection rates under 8%, comparable to established German manufacturers. Stephen had implemented rigorous testing at every stage: raw material analysis, molten glass sampling, annealing verification, optical property measurement, stress testing, durability confirmation. Any batch failing any test was remelted and started over. The factory operated in deliberate obscurity. No signs identified the build. Workers were told only that they were producing optical materials for defense purposes. Most didn't know exactly what their work was used for. Military intelligence maintained regular surveillance, ensuring no unauthorized visitors entered. Deliveries arrived in unmarked trucks. The factory's output went directly to government facilities that assembled military optical instruments. By December 1942, Stephen's operation had produced 2,347 kilograms of optical glass, enough for approximately 15,000 binoculars or equivalent optical instruments. The Department of Munitions contracted with Australian Optical Company in Melbourne and Commonwealth Engineering in Sydney to grind Stephen's glass into finished lenses and prisms. These companies had existed before the war, primarily serving civilian markets, but had struggled for materials. Now they had domestic supply. The technical achievement was extraordinary. Stephen had essentially recreated decades of German optical glass development in 9 months, working with unfamiliar materials under wartime pressure in a jam factory. He trained a workforce with no optical experience to produce military-grade glass. He'd improvised solutions to problems that would have stopped conventional engineers. The production costs ran approximately £3 per kilogram, compared to £7 per kilogram for American imports, when imports arrived at all. But the real test wouldn't occur in laboratories or production reports. It would happen in the jungles of New Guinea, on patrol boats in the Coral Sea, at coastal observation posts scanning for Japanese submarines, in the hands of Australian soldiers who needed to see the enemy before the enemy saw them. The glass that Stephen created would either perform under the worst conditions imaginable: tropical heat, torrential rain, constant humidity, rough handling and combat stress, or it would fail, and soldiers would die because they couldn't see clearly. The feedback would come from battlefields, from reports filed by junior officers who rarely knew or cared where their equipment originated, from survival rates and combat effectiveness statistics that reflected hundreds of small advantages or disadvantages. Stephen's glass would be tested not by laboratory instruments but by whether Australian forces could identify Japanese positions at 2,000 yards, whether coastal observers spotted submarines before they could strike, whether aircraft reconnaissance cameras captured usable imagery from 15,000 feet. That test was about to begin. The first combat deployment of Australian-made optical equipment occurred in March 1943, when binoculars manufactured with Stephen's glass reached the 214th Infantry Battalion fighting near Wau in New Guinea. The battalion had been operating with binoculars damaged during earlier jungle fighting, cracked lenses, delaminated optics, fungus growth between glass elements. Several sets had been completely destroyed. Replacements had been requisitioned months earlier but hadn't arrived due to shipping priorities. The new Australian binoculars reached Wau by air transport, one of the first supply drops prioritizing optical equipment. Lieutenant Robert Morrison, commanding a forward observation post, received a set on March 17, 1943. His after-action report, filed March 25th and archived in Australian War Memorial Collection AWM52, provides rare direct testimony about optical equipment performance. New Australian-made binoculars significantly superior to previous British issue, clarity excellent at maximum range, tested to 1,800 yards. No fogging in high humidity conditions that had ruined previous sets. Optics remained clear after 3 days of rain and mud exposure. Morrison's report noted something else. The Australian binoculars' optical quality matched or exceeded captured Japanese equipment. This represented a stunning reversal. For 18 months, Japanese forces had possessed optical advantages, their binoculars, rangefinders, and observation equipment consistently outperforming early war Allied gear. Australian soldiers had learned bitter lessons about Japanese ability to spot Allied positions first, to observe Allied movements from concealed locations, to coordinate artillery using superior observation equipment. Now that advantage was neutralized. By mid-1943, Australian infantry units, coastal defense positions, and naval vessels increasingly carried optical equipment manufactured from Stevens glass. The production numbers tell the story. 1943 total output reached 8,734 kilograms, enough for approximately 55,000 binoculars or equivalent equipment. Not every Australian soldier received new binoculars, but enough did that optical inferiority ceased being a systemic problem. The naval impact proved even more critical. Royal Australian Navy patrol boats, small, fast vessels assigned to protect coastal shipping and spot submarines, depended entirely on optical equipment for their mission. Radar remained scarce and unreliable in 1943. Submarine detection depended on sharp-eyed lookouts with excellent binoculars, scanning endless ocean for periscope feathers or surface submarines. HMAS Arunta, a tribal-class destroyer, received new Australian-made binoculars and observation telescopes during a refit in Sydney in May 1943. On September 22, 1943, operating east of New Guinea, Arunta's lookouts spotted a submarine periscope at 4,200 yards, at the extreme range of optical visibility. The destroyer maneuvered to attack position, forcing the submarine to dive, then prosecuted with depth charges. Post-war Japanese records identified this as I-19, which survived the attack but was forced to abandon its patrol. Arunta's captain, Commander J.C. Morrow, credited the early detection to superior optics, noting that previous equipment couldn't have resolved the periscope at that range in moderate sea conditions. Similar reports accumulated through 1943 and 1944. Australian coastal observation posts spotted submarines on 47 occasions, guiding patrol boats or aircraft to investigate. Not all sightings resulted in attacks. Some submarines escaped. Some sightings were false alarms. But the detection rate improved measurably once Australian-made optics reached observation stations. A classified 1944 Navy analysis, declassified in 1978, concluded that coastal observation effectiveness had increased approximately 35% compared to 1942 levels, attributing much of the improvement to better optical equipment. The arithmetic of submarine warfare is unforgiving. Spotting a submarine first might mean the difference between sinking it or being torpedoed by it. Even forcing a submarine to dive and abort its attack represented victory, as submarines needed to surface regularly to recharge batteries and couldn't effectively attack while submerged for extended periods. Every submarine forced to dive, to abandon patrol stations, or to operate cautiously was a submarine not sinking merchant vessels carrying supplies Australia desperately needed. Aerial reconnaissance provided another crucial application. RAAF aircraft conducting photo reconnaissance over Japanese positions in New Guinea, the Solomon Islands, and the Dutch East Indies required high-quality camera lenses to capture usable intelligence photographs from operational altitudes. Pre-war reconnaissance cameras had used German or British lenses. By 1943, these were wearing out. Fine scratches from dust and maintenance, coatings degrading from tropical conditions, mounting mechanisms loosening from aircraft vibration. Australian optical workshops began manufacturing reconnaissance camera lenses using Stevens glass in late 1943. The technical requirements were demanding. Lenses had to resolve detail at ground level from aircraft flying at 20,000 feet, maintain focus across temperature ranges from ground-level tropical heat to high-altitude cold, and function reliably despite constant vibration. The first Australian-made reconnaissance lenses entered service in February 1944. Photo reconnaissance analysts at RAAF Base Townsville reported marked improvement in image quality. A March 1944 assessment compared photographs taken with Australian lenses to earlier imagery of the same Japanese installations near Rabaul. The Australian-made optics delivered sharper images with better contrast, allowing analysts to identify smaller objects and discern more detail. One specific example. Photographs revealed individual artillery pieces under camouflage netting that previous imagery had shown only as vague shadows. This intelligence directly supported bombing raids that destroyed the artillery positions. The cumulative effect of these improvements, better binoculars for infantry, superior observation equipment for naval vessels, enhanced reconnaissance camera lenses for aircraft, was a measurable increase in Australian combat effectiveness. Quantifying exactly how many lives Stevens' optical glass saved is impossible. Wars don't work that way. But the trajectory is clear. Australian forces moved from optical inferiority in 1942 to optical parity or superiority by 1944. And domestic optical glass production was central to that transformation. Stevens' factory continued expanding. By mid-1944, the Marrickville facility employed 67 workers operating 3 furnaces producing optical glass around the clock in 3 shifts. Annual production reached 14,230 kilograms, more than double 1943 output. The factory had become the 3rd largest optical glass producer in the British Commonwealth, after facilities in Britain and Canada, and the only producer in the Southwest Pacific region. The production diversity expanded beyond initial crown glass. Stevens had successfully developed 7 distinct optical glass formulations by war's end. 3 crown glass types with varying refractive indices, 2 dense flint glasses for prisms, 1 special high-dispersion glass for achromatic lens systems, and 1 extremely hard glass for gunsight reticles that needed to withstand recoil shock. This variety allowed Australian optical manufacturers to produce increasingly sophisticated instruments without importing specialized glass types. Quality metrics remained impressive throughout the expansion. Rejection rates held around 7-9%, comparable to established manufacturers. No catastrophic quality failures occurred. No batches of systematically flawed glass reaching military users. Stevens' obsessive testing protocols caught problems before they left the factory. Workers who'd entered the factory knowing nothing about optical glass became skilled specialists capable of detecting subtle flaws invisible to untrained observers. The financial picture validated the investment. The Department of Munitions' total expenditure on Stevens' operation through war's end reached approximately £247,000, roughly $30 million in current terms. This had produced over 40,000 kilograms of optical glass, enough for approximately 250,000 binoculars or equivalent optical instruments. The cost per kilogram had dropped from initial £3 to under £2 as production scaled, well below American or British prices. More importantly, the glass was available when needed, not subject to shipping delays, submarine attacks, or competing military priorities. Japanese intelligence services never identified Stevens' facility as a strategic target, though they knew Australia had achieved optical self-sufficiency. Captured Japanese documents analyzed after the war revealed confusion about how Australia had overcome optical glass shortages so quickly. Japanese planners had assumed correctly that Australia possessed no optical glass production in 1941. They'd assumed incorrectly that this situation would persist, leaving Australian forces dependent on increasingly unreliable imports. A Japanese naval intelligence assessment from September 1944, translated and archived in Allied intelligence files, noted, Australian optical equipment quality has improved substantially from 1942 levels. Source of supply unknown but presumed American. Australian coastal observation effectiveness has increased, complicating submarine operations. The assessment recommended that submarines operate more cautiously near Australian coasts and avoid areas with known observation posts. This alone represented strategic victory, forcing enemy submarines to operate less effectively, because Australian observers could now see them. The broader strategic impact extended beyond individual combat encounters. Australia's ability to sustain optical equipment production freed American and British factories to focus on their own forces' needs. The approximately 250,000 binoculars worth of optical components Stevens' factory produced meant 250,000 fewer binoculars that needed to be manufactured in America, shipped across submarine-infested Pacific waters, and delivered to Australian forces. This represented shipping capacity that could be used for other critical supplies: ammunition, fuel, food, medicine, vehicles. In the grim calculus of industrial warfare, every ton of cargo not needed from overseas meant another ton of cargo that could be something else. Australia's domestic optical glass production, modest compared to American or German output, was nonetheless strategically significant precisely because it eliminated a dependency that had threatened to leave Australian forces literally blind in their own defence. VJ Day, August 15, 1945. The war ended, and with it, the desperate urgency that had driven optical glass production. Military contracts began winding down immediately. The Department of Munitions, facing massive demobilization and defense spending cuts, reduced orders by 75% within 3 months. By early 1946, Stephen faced a crisis as severe as 1942's technical challenges. What to do with a factory designed for military production in a peacetime economy that no longer needed military optical glass? Stephen's solution demonstrated the same practical creativity he'd applied to technical problems. He pivoted to civilian optical markets, camera lenses for photographers, telescope objectives for amateur astronomers, precision optical components for scientific instruments, industrial inspection lenses and specialized glass for medical equipment. These markets were smaller than military contracts had been, but sustainable. Australian photography boomed in the post-war years, veterans returning home with newfound interests in documenting their experiences and families. The market existed, Stephen needed to reach it. He renamed the operation Auer Optical Industries in 1947, registered as a private company with Stephen as principal shareholder. The military-era secrecy lifted. For the first time, Stephen could advertise, could acknowledge publicly what his facility had accomplished during the war, could recruit workers openly rather than through government channels. The workforce contracted from wartime highs of 67 to a peacetime core of 23, but those who remained included his most skilled specialists. The business thrived modestly. Australian camera manufacturers like KL and Asahi sourced lenses from Auer Optical. The University of Sydney commissioned telescope objectives for their new observatory. Industrial companies ordered specialized inspection lenses. Annual revenue reached £45,000 by 1950. Comfortable profitability, but nowhere near wartime production values. Stephen had secured his financial future, but would never be wealthy. Stephen's technical contributions received belated recognition in 1951 when the University of Melbourne awarded him an honorary Doctor of Science degree, citing extraordinary contributions to Australian industrial capability during the war and pioneering work in optical glass manufacturing. The ceremony occurred in June 1951, attended by former military officials and optical industry representatives. Ernest Burberry, by then retired, gave a speech describing their first 1942 meeting and Stephen's transformation from persistent letter writer to industrial pioneer. The citation noted that Stephen had published 3 technical papers in Australian scientific journals between 1948 and 1950, documenting optical glass compositions and manufacturing techniques. These papers, written in the precise technical English Stephen had mastered during his Australian years, represent the only detailed public documentation of his wartime work. He'd carefully omitted classified military information, but shared enough technical detail that other researchers could build on his foundation. His impact on Australian industry extended beyond his own factory. Several of Stephen's wartime employees left after the war to establish their own optical businesses or join existing ones, taking their acquired expertise with them. This knowledge diffusion seeded Australian optical manufacturing capability that persisted for decades. By the 1960s, Australia possessed a modest but competent optical industry. Camera lens manufacturers, telescope makers, scientific instrument companies that traced its origins partly to skills and knowledge that had originated in Stephen's wartime factory. The personal recognition Stephen valued most came from veterans. Throughout the 1950s and 1960s, former soldiers who learned about Stephen's role occasionally wrote him letters or visited his factory. These weren't official acknowledgements. The military establishment remained largely oblivious to individual contributions like Stephen's, but personal expressions of gratitude from men who'd used optical equipment in combat and understood its importance. One letter, preserved in Stephen's papers donated to the University of Melbourne after his death, came from Robert Morrison, the lieutenant who'd filed that March 1943 report about Australian binoculars. Morrison wrote in 1957, "I never knew during the war where our optical equipment came from or who made it. Learning now about your work, I wanted to express belated thanks. Good binoculars saved my life more than once in New Guinea by letting me see Japanese positions before walking into ambushes. Your work mattered enormously to those of us who depended on it. Stephen retired in 1963, at age 68, selling Auer Optical Industries to Commonwealth Industrial Gases, which continued operating the facility as a subsidiary for another decade before closing it in 1974. The site in Marrickville was eventually demolished. A residential apartment complex now occupies the location. No historical marker notes what occurred there during the war. The facility's contributions were too technical, too obscure, too far from traditional combat narratives to register in public memory. István Auer died on November 8, 1970 in Melbourne, aged 75. His obituary in the Age newspaper ran 3 paragraphs, noting his wartime contributions to optical glass production, but focusing primarily on his later civilian work and university honours. Most Australians reading the obituary wouldn't have understood the significance of what he'd accomplished. Even most optical industry professionals didn't grasp how close Australia had come to complete optical dependency in 1942, or how one immigrant's technical knowledge had solved that crisis. The technical legacy proved more durable than public memory. Stephen's optical glass formulations, refined through wartime experience, became the foundation for Australian optical glass standards codified in the 1950s. When Australian Standards Association published SS 2385 optical glass specifications in 1962, 3 of the standard glass types, designated as Australian Crown 1, Australian Flint 2, and Australian Special 7 inches, were essentially Stephen's wartime formulations with minor modifications. Engineers using those specifications rarely knew they were working with formulas developed in a converted jam factory during desperate wartime circumstances. The broader transformation Stephen's work represented, Australia's movement from colonial dependency to industrial self-sufficiency, continued accelerating in post-war decades. The lesson of optical glass applied to other industries. When supply chains collapsed, when traditional sources disappeared, when survival demanded self-reliance, Australia proved capable of developing domestic alternatives. This wasn't unique to Australia. Similar stories played out across Allied nations during the war. But each instance reinforced the principle that industrial capability could be built from nothing when necessity demanded and when the right expertise was available. Modern optical technology has long since surpassed wartime standards. Contemporary military forces use night vision systems, thermal imaging, laser rangefinders, and satellite reconnaissance technologies that would seem like science fiction to 1942 soldiers peering through binoculars. Yet the fundamental principle remains unchanged. Military effectiveness depends partly on the ability to observe the enemy better than the enemy observes you. The technology evolves, the principle persists. Australia's contemporary optical industry, modest compared to manufacturing giants but sophisticated in its capabilities, traces some of its lineage to Stephen's wartime innovation. Companies producing precision optical components for scientific instruments, medical devices, and telecommunications equipment employ manufacturing principles that Stephen helped introduce to Australian industry. The connection isn't direct. Modern optical manufacturing uses techniques Stephen never imagined, but the industrial foundation he helped establish created pathways for subsequent development. The refugee dimension of Stephen's story resonates particularly in contemporary contexts. He arrived in Australia fleeing persecution, carrying technical knowledge and determination, but few material resources. Australian society in 1938 wasn't especially welcoming to refugees. Prejudice and suspicion were common, but the immigration system recognized that technical skills had value. Stephen's subsequent contributions validated that recognition thousands of times over. The £127 in savings he carried through Melbourne Customs in 1938 became £247,000 in military production value by 1945, plus the incalculable strategic value of domestic optical glass supply. How many refugees carry similar knowledge, similar capabilities, similar potential to contribute? How many Stephens never get the chance to prove what they can accomplish because immigration systems don't recognize their skills or because societies don't provide opportunities? These questions extend far beyond optical glass or World War II history. They concern how societies identify, welcome, and utilize human potential, especially potential that arrives from unexpected places in unexpected forms. István Auer's story isn't a simple hero narrative. He wasn't a soldier who charged enemy positions. He didn't command forces or develop grand strategies. He solved a technical problem, an important technical problem, but nonetheless a problem invisible to most people then and now. His contribution was the work of months spent perfecting furnace temperatures and glass compositions, of careful quality control and systematic production expansion, of training workers and establishing industrial processes. This is how wars are actually won, through thousands of contributions like Stephen's, through the accumulated effect of engineers solving production problems, of workers maintaining quality standards, of administrators recognizing competence and supporting it with resources. The optical glass that Stephen's factory produced didn't win the Pacific War, but it contributed measurably, significantly, to Australian forces' ability to fight effectively at a critical period when they faced possible invasion and had to depend on their own resources. On that morning in February 1942, when lookout James Mitchell peered through fungus-infected binoculars at a sky that should have been empty, Australia's optical vulnerability was starkly visible. 18 months later, Australian forces used optical equipment manufactured domestically from glass produced by a Hungarian refugee in a converted jam factory. That transformation, from complete dependency to self-sufficiency, represents the kind of industrial achievement that shaped the war's outcome as surely as any battle. Dawn over Darwin Harbour today. The air hangs thick and still at 88 degrees Fahrenheit, carrying the smell of salt water and tropical flowers. Tourists peer through modern binoculars at historical markers explaining what happened here in 1942. The binoculars are probably made in China or Japan. Bitter historical irony. And they work flawlessly because optical glass manufacturing became a global commodity industry in the decades after the war. But on a February morning 83 years ago, when those Japanese aircraft appeared overhead and lookouts couldn't see them clearly through compromised optics, Australia faced a crisis that technical knowledge and determined innovation eventually solved. The solution came from an unlikely source, an immigrant who'd fled fascism with formulas sewn into his coat lining, who'd persisted through rejection until someone listened, who'd transformed a jam factory into a precision optical glass production facility. Against all conventional wisdom, István Auer's glass let Australian soldiers see their enemies, sometimes in war and in life. That's the difference between survival and catastrophe. Sometimes that's everything.